All right, Algebra 1, welcome back. You should have just finished your activity looking at two different people's job offers, kind of, or sort of how much money you will make with these two different jobs and their different rules. One was a linear styled function, one was an exponential style function, and we're going to use this as our stepping point into exponential functions and what they look like. All right, so at the beginning of the year, we talked about how there's three function families that we talked about in Algebra 1. We had our linear function, which we spent a lot of time at the beginning of the year on. We have our exponential function, which we are just going to start, and then we have our quadratic function, which we will look at towards the end of the year. Now, they all have their own distinct shape that comes with their parent function. So our linear function, once again, was that line. It was y equals x was its parent function. Our exponential function, they have this designated curve or the very distinct shape curve fast rate or at down at a very fast rate. And the parent function for that, it might be hard to see, but it's y equals 2 to the x power. And then our quadratic function, which is this shape, which we often see is our quadratic, which has the parent function of y equals x squared. But we are going to look at exponential functions today. We're going to talk about those. So we're going to kind of do what we kind of just did in your Desmos activity, but we're going to compare linear functions, exponential functions to start with. So let's say we have the two functions y equals 2x and y equals x, or y equals 2 to the x. So they sound similar, but they're different. One has x as the exponent, one has x as the variable or the multiplied by your coefficient. So in our y equals 2x, we have 0, 0, 1, 2, 2, 4, 3, 6. So we know that consistent pattern where our slope, as we increase, we're always adding 2 every time. That's our slope. That's that constant rate of change. We know our y-intercept is going to be 0 because we don't have a b in our function. It's as if I had plus 0, so my y-intercept is 0. With our other function, though, our exponential function, we have y equals 2 to the x. Now, looking at this function, y equals 2 to the x, I have, if I plug in 0, we know y would equal 2 to the 0. I'm changing that exponent. Well, what's any number to the power of 0? Well, anything to the power of 0 is always 1, so we get y as 1 or output. If I have an input of 1, it would be y to the 2 to the 1. Well, 2 to the 1 is just 2. If I change it to 2, we know that's 2 squared is 4. If I change it to 3, 2 to the third is 8. So if we look, what's happening here, our exponential function is multiplying by 2 every time. Instead of adding by a constant value, we're multiplying by a constant value. We're multiplying by a consistent rate. So we started at 1, multiplied to 2, multiplied to 4, multiplied to 8, and we could keep going. 16, 32, 64, and we could keep going and going and going and keep multiplying, and we're getting bigger and bigger and bigger at a much faster rate than our linear function is. We can see that as well on the graphs of these two functions. So here I have a graph of my linear function. We know it has that constant slope, that rise over run. I'm going up 2 over 1, up 2 over 1, up 2 over 1 every time. And that's consistent throughout the entire line. Versus my exponential function, if I look at it, starting from my point at 1, going to my next point, I'm going up 1 over 1. But the next time I'm going up 1 over 2. Or sorry, up 2 over 1. And the next one I'm going up, you can't really see it, but it goes up 4 over 1. I can even do this backwards. I'm going over 1, down 1/2. Over 1, down 1/4. Over 1, down 1/8. It's getting even smaller and smaller every time. So we get very small, 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 and we're growing by 2 times every single progression. Now, our pattern or our basic formula for our exponential function is y equals a b to the x, where a is the y-intercept and b is the rate of change. So those are the two pieces that we need to know for this pattern. And luckily, unlike linear functions, there is only one form of an exponential function. It's pretty much just this. This is what you need to know. You don't have to know multiple different types of forms. So y equals a times b to the x, where a is y-intercept and b is the rate of change. So let's say we had y equals 2/5 to the x. Well, 2/5, if I were to fill out this table, this would be y equals 2 times 5, where x is 0. Well, 5 to the 0 is just 1, so this would just be 2. If I change my input to 1, it'd be 2 times 5 to the 1. Well, once again, 5 to the 1 is just 5, so this is 2 times 5, which is 10. 2 times 5 to the second would be 2 times 5 squared, which is 2 times 5, or 2 times 5 squared, or 2 times 25. Let me change that. Which is 50. 2 times 5 to the third would be 2 times 125. 125, sorry, not 150. Which would give me 250, sorry. And if we look at this pattern, we see that same rate of multiplication. Once again, we're timesing by 5 every time. Times by 5, times by 5, times by 5. Every time I'm multiplying by 5, I could then multiply 250 by 5 again, and this would give me my next term, and I could keep going and going and going. It has that constant multiplication. It's not necessarily a rate of change, or it is a rate of change, but it's not necessarily the same idea as the slope where I'm adding, but I'm multiplying every time. And once again, we said the A is our y-intercept. So 2 was my y-intercept. I started at 2. When x is 0, that's when we hit our y-intercept. And my rate of change was b, my 5. That's what I multiply every time. So without even having to calculate anything on this, I can easily fill out my table. I know my y-intercept is my a, which is 16, the number in front. And then I'm multiplying by 0.25 every single time. That's my rate of change. So 16 times 0.25 is 4. 4 times 0.25 is 1. 1 times 0.25 is 0.25. And I could just keep going and going and going with that consistently. Let's look at 2 other examples. -4 times 2 to the x. All right. So we know, once again, our y-intercept at 0 is always at a, the very first number. So that's going to be -4. Well, I'm multiplying by 2. -4 times 2 is -8. -8 times 2 is -16. -16 times 2, I'm sorry, is -32. So this one's actually a little bit different. Rather than increasing very quickly, this function is actually decreasing very quickly. It's getting larger and larger negative numbers. So essentially, it's going down instead of going up as an exponential function. Oh, I lost my thing. Last one. -16 times 0.5 to the x. So I know I'm going to start with my first number, which is -16. My rate of change is 0.5, so I'm multiplying by 0.5. Well, -16 times 0.5 is -8. -8 times 0.5 is -4. -4 times 0.5 is -2. With this one, I'm actually decreasing. My number is getting smaller and smaller and smaller and smaller. So we have two essential types of exponential functions. They can increase, we call that exponential growth, and they can decrease, we call that exponential decay. And depending on whether that y-intercept is a positive or negative value, might mean on whether we're growing positively or growing negatively, or we're decaying positively or we're decaying negatively. If I look, this function is actually getting closer and closer and closer towards the negative values compared to getting closer and closer, or getting farther and farther down, as my first function was. It was getting deeper and deeper into the negatives, but this one actually is getting closer and closer and closer towards 0. If I were to multiply this again, it'll get -1, -0.5, -2.5. I'm getting closer and closer and closer towards that 0 value. So let's look at a bunch of equations and Desmos, and let's make predictions and patterns based off what we see. So I'm going to look at an equation, and we're going to try to figure out what we think that equation is going to look like. So I have, let me put this on projector mode. All right, so I have y equals 4 times 5 to the x. So I assume my y-intercept is going to be 4, and I'm going to be increasing because my rate of change is a positive value. Or my rate of change is a whole number. So here I am. I'm crossing my y-intercept at 4, and I'm increasing at a pretty steady rate. If I look at this next one, I assume I'm going to be crossing at 6, but my rate of change is a smaller number. It's only 2, so I'm going to be increasing at a slower rate. So there our red line is. If we look, it's a little bit flatter. It's not as steep, so we're increasing at a more steady rate with 6 as our y-intercept. This one I have a y-intercept at 3, and I'm multiplying by 1.5 every time. So once again, this is an even slower rate of change. So we're even flatter that time with our rate of change. And then 5, 8, this is the steepest rate of change so far with a rate of change of 8, but we're increasing, or we're passing at 5. And this last one, y equals 1 times 200 to the x. So this is basically going to be a vertical line because multiplying by 200 every time, that's a very, very, very fast rate of change. And we're passing at 1. So if you see that purple line, it's almost like a right angle. If you look at it, very steep. So let's look at a second set. All right, y equals 2 times 0.5. So if I look at 0.5, I know when we had 2 times 0.5 before, we were decreasing. So this is actually a function that's going to start large and end small. I'm getting smaller and smaller and smaller, closer and closer towards 0. For 0.75. 0.75 is a little bit larger than 0.5, so I'm not decreasing as quickly because I'm multiplying by a larger number, because I know if I multiply as a very, very small number, I get smaller and smaller much quicker. Like this one, y equals 3 times 1/3. 1/3 is a small number, so I know I'm getting smaller and smaller. My y-intercept is 3, and I'm getting small very quickly. Same with 0.25, we're getting smaller even faster. And then 0.17 is the smallest possible fraction we have in this example. So we should be decreasing at the fastest rate of change. And once again, that number in front is always going to be our y-intercept. So look at one last set. Y equals -3 times 4 to the x. So when we saw earlier, when we had a negative y-intercept, I know I'm going to be passing out here, but I'm multiplying by 4 every time. So -3 times 4 is -12. So I'm going to get deeper and deeper into my negative. So I'm going to be zooming down with this one. Y equals -2 times 5 to the x. So it's a larger rate of change. My y-intercept is -2, so I'm going to be going down even faster, but my y-intercept is going to be only at -2. Y equals -5 to the 100, so I'm going to be zooming down very, very fast because we're multiplying by 100 every single time. And then y equals -4 to the 0.5. So once again, we saw when we had 0.5 or those decimal rate of changes, we were getting closer and closer towards 0. We were getting closer towards our x-axis compared to getting farther away from our x-axis. So this one's going to start at -4 as my y-intercept, but it's going to go towards 0 compared to going towards -infinity. And then same with -3 times 0.25. I'm going to get closer and closer towards 0 instead of -infinity. All right, so now that we have a little bit better idea of what some of these look like, let's see if we can predict what these last three are going to look like. Y equals 16 times 3 to the x. So knowing my general consistent pattern with functions, if I have an axis here, I know I'm going to be crossing my y-axis at 16, and I'm multiplying by 3 every time. So I know I'm going to be multiplying by I'm going to be multiplying, so I'm going to be growing. 16 times 3 is going to give me a bigger and bigger and bigger number every time. So I know I'm going to be going up with a y-intercept of 16. Y equals 10 times x, or times 0.5 to the x. So this one, I know my y-intercept once again is going to be at 10, that number in front. Multiplying by 0.5 though. So I know when I multiply by 0.5, I'm getting smaller and smaller and smaller every time. I have a fraction essentially. So I know I'm going to be getting closer and closer and closer towards 0. I'm going to be decaying with this function. And the last one we have, y equals -4 times 3 to the x. So it's -4. Well, -4 I know is going to be below my x-axis. So I'm going to be passing down here, but I'm getting multiplying by 3. So -4 times 3 is -12. So I know I'm getting deeper and deeper into my negatives with this function. So I'm going to start close towards 0 and then go farther and farther down. So even just by looking at the function, even without having to graph it, we can get a general idea of how the exponential function is going to be shaped, whether it's going to go up, go towards 0, or go down towards negative infinity. We can get an idea of where that y-intercept is and what that rate is. So let's look one last question. So which statement about the graph of y equals 8 times 0.25 raised to the x is true? The x-coordinate is of x, or the coordinates of the x-intercept are 0.25 times 0, or 0. The coordinates of y-intercept are 0, 8. The equation of the asymptote is x equals 0, and the graph includes the point 2, 1. So let's figure these out. Well, is the coordinate of the x-intercept 0 or 0.250? Well, we know in order for all we need to do in order to check this x-intercept is let's plug this into our function. So if we have 0, this would equal 8 times 0.25 raised to the 0.25. I plugged in my x and my y, and I want to see if this is true. One thing actually we can think about, looking in all these examples, all those examples in all of these different sets that we had, none of these functions ever actually touch 0. None of them are ever actually reaching 0. We have some functions that look like they're getting very, very close, but if we kept zooming in and zooming in and zooming in on these, we would actually see that none of these functions ever touch 0. They just get very, very close. We can keep zooming in, and we can see there's always going to be a gap in between 0 and our function. And the reason being is if I multiply by 0.2, and then multiply by 0.25, and multiply by 0.25, and multiply by 0.25, and multiply by 0.25, I'm dividing something in tinier and tinier pieces. And those pieces are going to get exponentially small. They're going to get super, 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 super small, but I'm still going to have always something there. I'm going to have a smaller and smaller and smaller and smaller, smaller number. That number is going to be very, very close to 0, but it's never actually going to equal 0. So is it possible for our y-intercept or our x-intercept to actually happen, to ever actually touch the x-axis? No, because an exponential function is never actually going to have an x-intercept. It's never actually going to touch x equals 0 unless we have some other thing affecting the function. But this is impossible, so we actually won't have that. Another thing we could have done is we could have plugged this into the calculator and saw that this doesn't actually equal 0, so we know that's not true. Are the coordinates of the y-intercept 0, 8? Well, we know our y-intercept is always the a value of our y equals a times b to the x. So in this case, 8 is our y-intercept, so we know that one is true. Let's just prove that these other two aren't true, and let's just talk about them really quick before we end out our day. So the equation of the y-intercept is x equals 0, or the equation of the asymptote is x equals 0. So that funny word there, asymptote, what that is if we look at these exponential functions, they all have a consistent pattern where they get super, super close to a line, and then they sort of like shoot away from it. So we were either going up, or we were going down, or we were getting like super close to 0, or we were starting really high and getting... Those were like the 4 different patterns we have. If we look, all of these functions don't touch this. I haven't used green. This line right here, our x-axis. That is what's called an asymptote. An asymptote is essentially a line that a function can get very, very, very close to, but never ever actually touch. So like what we talked about in that last part already, we're never actually going to touch x equals 0. We're just getting very, very close to it. Or we're never actually having an x-intercept. We're getting just super, super close to that x-axis. But the thing is, the equation x equals 0, I'm thinking where are all my x values equal to 0? Well, that is my y-axis. So is that true for an asymptote of our function? No. And then lastly, the graph includes the point 2, 1. What we could do for this is we could just plug in the numbers 1 in for my y, and then 2 in for my x, and we could see if that's true. So 0.25 times, or raised to the second power times 8. Let's plug that into the calculator. Let's see if this is actually true. 0.25 squared times 8. Oh, I plugged that in wrong. I'm sorry. So 0.25 squared, let's do that. That is 0.0625. Let's multiply that by 8. Let's see if this actually equals 1. Times 8 is 0.5. So we have 1 equals 0.5. Is that true? No. So we know that one is also false. But we already figured out that the coordinates over y-intercept are 0, 8. So that's where we're going to stop it for today. You're going to have a Desmos activity where you're going to work a little bit more with exponential functions and sort of practice predicting what the pattern is going to look like and what the shape of these functions are going to be. And we're going to continue talking about these in the future. So let me know if you have any questions over this. Other than that, have a great rest of your day.